in the presentation. So we talked about stars like our sun, that how they evolve, and I'm just gonna go quickly over the slides. So the main factor in any evolution of any star is the mass, which controls gravity. Gravity controls density of the hydrogen in the core. That in turn controls how quickly, how frequently particles will accelerate, collide, and be able to react, fuse together. The mass also determines availability of the fuel. Density also controls the speed of the reaction. So more massive stars will evolve faster, low mass stars will evolve slower. Fuel availability basically tells us about how quickly the star evolves and goes through the changes from like main sequence to outside of the main sequence. We talked about hydrostatic equilibrium. There's a competition of between two forces: inward pull of gravity and outward push of pressure caused by heat, right? There's a pressure, you can use gas laws to figure it out. It's approximation, but it will work for the plasma inside the core of a star. And when these two are balanced, the star is in hydrostatic equilibrium. When it's not balanced, star will either shrink under the force of gravity, overcoming external outward pressure from the core, or it will expand if the pressure is higher and the gravity is lower, or gravity is low but pressure is higher than gravity. We talked about, well, I showed you the slide where these two forces are represented by arrows. And we know initial stages are pretty much the same. We have rotating nebula that comes from interstellar medium. It becomes denser, turns into protostar, and temporarily it's going to be stable. And then at that moment, the core, the central part of the star, will continue shrinking and forming a star, regular, star, and then outside of the protostar will be forming an accretion disk eventually. A pre-main sequence star is a star that will start fusing hydrogen into helium, and this could be observed from a distance by looking at the bipolar outflow. So these are two flows of stellar wind, early stellar wind, coming out in polar directions, right? Even though the star emits particles in all directions, probably almost uniformly, particles that are going through the accretion disk will have much harder time getting through, while particles going through the polar regions, which are already cleared, will have easier way out. And as they travel through interstellar medium, they eventually collide with the denser regions, and when they collide, they give off light, and this light could be detected. And based on this sign, we can look for the location of a newly forming star. Once the star clears its surrounding, blows away the gas, the dust, or planets form and then clear the surrounding in the accretion disk, then the star will become clearly visible. It is still not quite there yet. It will continue shrinking and brightening, and eventually it will reach the main sequence. So the slide that shows HR diagram shows you a cloud shrinking, forming a protostar, and then forming pre-main sequence star, and finally reaching the main sequence. Stars spend most of their life in the main sequence, in this stage of hydrostatic equilibrium, and very little changes happen within the star. Hydrogen is available, it's fusing, heat is emitted, more or less stable amount of heat, and there are basically no fluctuations, like radical fluctuations of luminosity of the star. However, gradually, over a long period of time, in case of our star, it's about 9 billion years, the star will become brighter and brighter, reaching, according to models, about twice as much brightness by the time it's going to drift away from the main sequence. The main mechanism by which the star produces energy is by fusing protons with protons. So hydrogen plus hydrogen becomes helium. And the different mechanisms of reaching helium, we'll talk about them separately. So eventually, stars like our sun will drift away from the main sequence. They spend roughly 8 to 9 billion years. We can round this number to 10 billion years on the main sequence. When hydrogen runs out from the core, right, the core shrinks because there's less pressure outward. And when it shrinks, it emits light energy that will push the outer layers away. And thus the outer layers expand. And as they expand more than the energy provided to them. And as they move away from the core, they cool down. So it's like expansion of gas will cool it down. It's almost like gas laws, basically. When you expand the gas without providing it extra energy, it will cool down. So this stage is called red giant phase, and it lasts about 1 billion years. The star, like the sun, will expand by a few hundred times, and it could affect motion of nearby planets. But some models show that Earth probably will be fed, meaning that it will continue moving along its orbit. Maybe even it will be pushed a little bit away from the sun. Next, we went over helium flash. So helium flash is a result of increasing pressure in the core. Helium essentially is the product of HH cycle, and it's not fusible at the temperatures that are present right now in the sun. So this helium will accumulate over a long period of time, and then when the core shrinks, the density and temperature in the core may reach 100 million Kelvin, which is enough to start fusing helium. Fusion of helium is triple alpha process, meaning that 3 alpha particles should collide at the same time. And this releases enormous amounts of energy, and the star will brighten up. However, as a result, it will also lose outer layers, and basically the size of the star becomes smaller. Brighter means higher temperature, right? In this case, and smaller means lower luminosity. So even though it's brighter in terms of the appearance, yellow star will become yellow, but it will become yellow giant star. However, it's going to be smaller than the red giant phase, and as a result, from a distance, it will look less luminous. Triple alpha process is very low probability event, and in order to increase the probability, you need to increase pressure and temperature. So when you do so, what happens is that collisions, number of elastic collisions per inelastic collisions increases, and inelastic collisions result in fusing of helium nuclei, alpha particles, into one carbon-12 nucleus. And this carbon then becomes the product, and it will be accumulated in the core. And the temperature is also high enough for the outer layer to fuse hydrogen into helium. So we have double structure. The inner core fuses helium, dumps carbon into the inside into the center of the core. The outer core fuses hydrogen and dumps it into the inner core, providing inner core with helium for fusion reaction. We looked at the HR diagram and then how the sun drifts from the main sequence to the red giant phase to yellow giant phase. And the amount of helium will fluctuate. And in case of a star like our sun, this period can last 100 million years. And as helium is used up, then the star will again go to the red giant phase, and may go back and forth a few times. And eventually helium will run out. So helium will be used up. Hydrogen is still available, but the problem is that the temperature and pressure are not high enough to continue fusing hydrogen into helium. We talked about thermal pulses, so I right now on slide number 18, right? And this changes of the brightness due to the availability of the helium for the triple alpha process changes the brightness of the star, and then that results in thermal pulses. So thermal pulses are processes that, or rather, these are telltale signs that the star is at the very end of its lifespan, and the next stage will be basically the last stage. So next slide in PowerPoint should show you how red giant shrinks into yellow giant and goes back to red giant, but unfortunately I cannot show that to you. So when all this fuel is gone, right, what happens is the core finally shrinks one more time. It is very hot. It's about 100 million degrees Kelvin. However, it doesn't have helium to fuse it. So since fusion stopped, the core will contract, which will heat it up again. But this time it's primarily made of carbon, and it's not enough. Temperature is not high enough, and pressure is not high enough to fuse carbon. Remember, it all depends on the mass. So the mass of the core, the innermost core, is not high enough to fuse carbon. This contraction of the core will emit enough energy, enough light and heat to push the outer layers one final time outside the star. And this push basically removes the outer layers. The star will lose the outer layers. Now, in terms of the mass, yes.
Your mic isn't working well.
Is it breaking up?
Yeah.
Maybe internet connection. I don't know. Maybe I should get a cable, something. But I'm recording. So this will be on YouTube, so you should be able to see it again if you missed this part. Okay.
Okay.
So if you notice something lagging, like really like bad, just shoot me a line in the chat box. I'll see it right away. So what we have here is that the outer layers do not have a lot of mass. So most of the mass is within the core. So the star will remain pretty much the same mass. Maybe we'll lose 10%. Okay, so let's see. I don't know what's going on, this stupid internet Wi-Fi. Let me see. Okay, can you guys hear me?
Yeah, you cut out for a bit, but you're back.
Yes, the room went dark, literally. Okay, so let's see. I think it stopped recording. No, it is recording. Okay, that's awesome. I don't know how to edit the videos, but whatever I get, I'll post it on the Google Classroom. So let me go back to sharing the. I think I had a hard time sharing the video with all parties. So I'm gonna continue this. So I was on the slide number, which one was it? It's called Fuel is All Gone. I don't see the number. Oh yeah, I see number 21. So basically, at this point, the star will expand beyond Martian orbit while still resembling a sphere, right? So the next slide, you see like a picture of that. And then basically after that, it's no longer following like spherical symmetry. Other forces will come into play. Local gravity plus gravity due to the other stars, nearby stars. Coriolis force will have some effect because star was spinning, and this spinning will affect the way the gases will be distributed. And so we get to the slide number 23, which is called planetary nebula. So within a few million years, the sun will shed its outer layer, and it becomes the outer layer is still very hot, so it will glow, and you can detect this by using regular telescope. And a lot of these objects were detected long before people understood what they were, and they were misinterpreted, so they were called planetary nebula. It's one of those misnomers. So planetary nebula is not the one that will, form planets. So next slide, you see, I think it's called cat's eye. And what you're looking at is outer layers of the star moving away from it. And then the brighter yellow-green regions, which is where the outer layers are moving away from the star and then colliding with interstellar medium. And as they slow down, they give off brighter light. The reddish glow is coming from really hot hydrogen gas. So it's heated up to a few thousand degrees, but it's very diluted also, right? And in the center, you see a really bright bluish white star. You can still call it a star, but it's no longer fusing anything. It just has residual heat, and it's hot enough to emit visible part of the spectrum. This is not supernova. No, it's just it's a very quiet process. It doesn't go explosively, and these layers move. Even though they move pretty fast, they're not moving at the speed that would be, in case of supernova explosions. So the next few slides show you different examples of planetary nebula. All of them have some sort of symmetry. Not perfectly spherical symmetry, because as they move, the layers, as the hydrogen moves away, the gravity is not even throughout. So there may be pockets where gravity will be stronger, and that would affect the motion of the surrounding hydrogen. So you will have some turbulence going on, and like structure will not be perfectly symmetrical. The next slide shows you almost perfectly symmetrical shape. So we probably are looking from the polar region. We're looking at the polar region of the star. If you're looking at the star at the angle, then it will look like the first image of the cat's eye. So in this case, the axis of the star rotation is tilted, and we're looking at the angle at the star. The slide 27 shows artist's rendering of how this could look like from Pluto's orbit. The reason it looks like a ring is that Pluto's orbit is tilted by 17 degrees. So, but I think it's not quite correct actually, because the gases will expand in all directions with slightly higher speeds along the ecliptic, the plane of the ecliptic, and slightly slower speed, in the polar regions. But I don't think you will be able to see like a disk. Probably it will be more like a gigantic cloud, more or less spherical, or like close to spherical shape. So if you go to the next slide, 28, in that case, you will see that the star has now drifted away from the red supergiant phase drifting away and forming a planetary nebula. So the top of the image shows you, the graph shows you ejected gases. The core continues shrinking since it doesn't have a fusion mechanism, and it slowly drifts away. It's a very slow process because the surface area of the star is quite small, so we'll lose heat slowly. And eventually it will cool down, and its temperature will go down, luminosity will go down. The reason it remains really bright right after it ejects all the gases is that it's really hot, extremely hot, 100 million degrees on the surface. So it should look like bright white bluish star. And then when it starts cooling, then it will lose temperature and luminosity will drop significantly. And eventually the white dwarf will cool so much that it will no longer be visible. So it says in a fairly short period of time, the planetary nebula fades away. And then what we have is a white dwarf, which used to be the core of the star, visible. And temperature of the surface, as I mentioned, is 100 million degrees. Next image shows you comparison of the size of the sun today to the white dwarf and to Earth. So it's comparable to size of Earth, slightly maybe larger than Earth. And the core of the star, which is right now is about 200,000 kilometers, will shrink to about 15,000 kilometers in diameter. Really small.
I have a
really
question.
dense. Question, yes.
I have a question about white dwarfs. So obviously they're like not going to be as dense as like a neutron star, but are they like still pretty dense?
They're very dense. Yes, you can calculate. You can take the whole star and shrink it to this size. It gives you the idea of the magnitude of the density. So I don't remember the number, but like it's a very high density. Thus, it's going to be really high gravity, surface gravity. There may be a number here on the slideshow. I just don't remember the number. So the question is, what white dwarf is made out of? Now, if you remember, the final product of the fusion was carbon. It's not going to be pure carbon because the other the other nuclear reactions that are taking place. There will be a little bit of oxygen, a little bit of nitrogen, maybe bits of lithium and something else. So it's not going to be perfectly pure carbon. But under the high pressure and high temperature, carbon turns into a diamond. So whenever you hear a song about Twinkle, Twinkle, Little Star, right? And what was that? I wonder what you are. And like diamonds in the sky. And that's basically is the truth. Meaning that those stars, at least the stars that completed their cycle and the mass comparable to the mass of the sun, will eventually turn into enormously large diamonds. A very beautiful color, probably bluish color because oxygen will give off bluish color, but they may be a tint of other colors as well. And the answer to a question about gravity is right there. So it's going to be about 200,000 times denser than Earth, and the density of cubic meter, 10 billion kilograms. Okay, to compare to Earth's, what's it called? Density of Earth is roughly 5,000 kilograms per cubic meter. So enormously dense object. Okay, so somebody in previous semester classes, well, everybody, in every class I have someone asking, can we just go and, mine the diamonds? So if you have that kind of question, you can also think about when you go there, you can have the whole diamond for yourself. The problem is you won't be able to come back. You will be attracted to this diamond so much, it will become your precious, and you won't be able to give it to anybody. Gravitational attraction will be roughly 200,000 Gs. G should be actually lowercase, I think, gravity of Earth. So anything that will be on the surface will be just flattened. Now, if this kind of stuff becomes a rogue star, meaning that if with interacting with other stars, it will be slingshot out of its system, it may become disruptive to other stars. So it's quite small, but it still has a lot of gravity. And if this kind of stuff would fly even like, you know, a light year away from the sun, that would be quite disruptive to the solar system. Because what those stars can do is they can move the stuff from the Kuiper belt or from Oort cloud, and this could create conditions where like asteroids or comets may be pushed into the solar system. And that could be disruptive to planetary motion, that could be disruptive to life if there's such thing, or you know, in this planetary system. In case of solar system, obviously it could be pretty problematic for us. And finally, a black dwarf. It becomes a black dwarf because it becomes so cold, it does not give off any light, right? And as a result, it should not be visible, which is even more scary, because if you're flying through space, if you have like star map, and you did not know that there was a star there a few billion years ago, then you may overlook that. And if you don't have like gravity telescope, you will not see the star. And that's a pretty dangerous thing. So black dwarf, this is slide 34, may look somewhat like that. Again, I'm not sure. This is like how artists see this. If it has a little bit of light or a little bit of you know, heat in infrared spectrum, you should be able to see it. But other than that, if it's really cold, it will just blend with the backdrop of the cold space. So slide 35 basically shows you that white dwarf, the bottom left, right? As it loses heat, it will drift to the right of the screen of the graph and become invisible. Larger stars, we'll talk about them in a different slideshow. Are there any questions?
For black dwarf, how is that like separate from, or does that become a black hole? How are those related?
No, not at all. Black dwarf is black because it's so cold it cannot emit its own light, visible light, right? But it has nothing to do with black hole. The reason they're both called black is that they're not emitting light. But black dwarf is made of regular matter, while black holes are not made of regular matter, and they have completely different mechanism of forming, and they are much more different in their masses. So it's a completely different thing.
All right.
Okay. Any other questions?